We covered the history of CNN. I hope it was instructive, because usually it's better to know how this system was developed, what were people thinking, what they've tried, because nothing just comes and in full-fledged form, ready with all bells and whistles. The way those bells and whistles are added usually helps to understand how the full system functions and maybe what it's missing and where you can contribute. So now let's look at the building blocks of convolutional neural networks, so you kind of know all of the tools in the toolbox, and then you can understand how special versions of CNN works. And we will start with what you already know is the convolution itself. So we have a kernel right here, and I think I have a new tool I can use. So this is the kernel, convolutional kernel, and this video shows you how this kernel is slid across the input. It could be input image if it's the input layer, or it could be input channel from the previous layer. This is the input, let's call it X, and this is the output, let's call it channel. We're not doing anything right now in this process. Here on the right, the same process is represented in 3D. So this is a lower level I, and this or layer, and this is I plus 1. But what is missing here? Actually, let's move and look at same thing. Convolution is represented here. So step by step. One. This is step 1, step 2, step 3. So our kernel, you can see it here, 0, 1, 2, 2, 2, 0, 0, 1, 2, is multiplied by whatever is overlaid, whatever it's overlaid of. What is actually happening, and I want to stress that now. Well, of course, everything is just matrix multiplication, but conceptually what we have is connections like that. Each has a weight. Those are the weights here. So some weights are 0. This, like this one, weight equals 0, right? For this guy, the weight equals 2. So those inputs go through, multiply by the weights, arrive here, get summed up, and then push through nonlinearity. Let's say it's sigmoid, but let's call nonlinearity sigmoid here. Well, let's rename it to something phi. Sum of all of those products, W times input with respect to I. And that's what is written here. The example, of course, doesn't have any nonlinearity, so you could see what is exactly happening. And step by step, 3, 4, 5, 6, 7, 8, 9, we eventually scan through the whole image. in this particular example, the step from here to here when our kernel is shifted by one step, and this step is called stride, and it doesn't have to be one, but in this particular case it is one. Notice in this example we start with the top left corner and align our kernel or our filter with the image and slide it from left to right. But is it the optimal way, or is it always the optimal way to do it? So it turns out it's not the only way or the optimal way. As you see here in this example, notice we are scanning our filter, our kernel, along a larger image than our actual input. What we've done, we've padded our image with zeros such that our kernel on this corner aligns in a way that the center of our kernel is the corner image itself. So this particular padding style is called same for short. What it means is that the image that is produced, the output channel, under, like this is 1 and this is, say, C, the center. So the C in the input will correspond to the C in the output. Sometimes, though, we'll talk about it more in just a second. Sometimes we want a situation when we gave a chance to each of the pixels. Even we want our kernel to participate or to scan in a way that it starts with handling one pixel at a time and only then eases into the image. And this convolution or padding style is called full. Let's look at why or how exactly this style that's called same works. This is the same video, just expanded. So look, in the beginning we are producing a pixel that corresponds, well, this image is actually not most accurate, but this pixel corresponds to this pixel in the channel. The output channel corresponds to this pixel in the input channel. And in fact, even though I copied this from this guide, copied this figure from this guide, the dimension should be 5, right? The same exactly as the input dimension. That's why it is called, the style of padding is called same. We will find it later very useful for operations or tasks such as segmentation, when we need to produce a mask or we need to produce a label for each pixel in the input image. So our output should be pixel perfect to the input image. But you get an idea. You can pause and stare at this picture, but just notice that there's slight discrepancy. Although yes, the center pixel does correspond to the center pixel in this figure. So how do the channels look? So now we have a convolution. You understand how it works. It's basically just a vector product. You can think about it, but as I said, for efficiency in actual implementations, those kernels are shaped together in a matrix, and so we multiply a kernel matrix of kernels by an image. Matrix multiplications are efficient, and CUDA kernels, GPU systems are very efficient in handling large matrix multiplications in parallel. This matrix is also called circulant. That is when the kernel actually is rotated through the rows of the matrix. But let's slide aside. You can understand that, you can read about it, or just do it manually if you don't understand how a kernel is multiplied by an image, or how the image is filtered, right? 9 pixels in the input image turned into 1 pixel in the output image by being filtered. So if our input image is this photograph of a person, a lady, then, and we have 14 neurons. Okay, that is important. Then how does the first layer look after those neurons have scanned through this image? Here's an example. This is layer 1. We have for each neuron, and each neuron, say, is a 3x3 filter. So we have a 3x3 filter with specific values for each of those images. And when this 3x3 filter was scanned with the original picture, this output is closest to the original picture than the rest. So when it was scanned with it, as those animations have shown in the same manner, this is what the first neuron produced, the first filter. And correspondingly for all of them. Usually we draw those 16 filters when we look at the diagram. We draw them, or the 16 outputs from 16 corresponding filters. We draw them like that, just to stress out that they're still two-dimensional. And say this is the input. The input could be RGB channel, which was RGB in this case. The picture was colored RGB, and then processing, and then next processing. So how did RGB get there, right? Notice this first. When we convolved one-dimensional or two-dimensional flat image, this is the videos that you just seen. But when we are convolving something like that with RGB, then what we're doing with our 3x3 filter is this. Our network is now our filter now has 9 times 3 parameters for each of the channels. There are respective parameters. The same happens here. For the next layer, we pierce with this block, sort of figuratively, and we scan this whole block such that our filter considers together and merges together in our weighted sum, followed by nonlinearity, all of the channels in the previous layer. So when all of these channels are pierced and put together by 27, I think 27, let's check. Yeah, 5 times 5 plus 2, yes, 27 neurons or filters, kernels. We get those channels, and this did use max pooling. Notice our filters get smaller and smaller, and I will talk about max pooling just in a little bit. So, and you see some filters are paying more attention to the eyes, some paying more attention to the mouth, and some paying more attention maybe to the the skin silhouette, well, this not silhouette. Some of them are silhouette, but I don't see it. So different thing pays attention to different parts of the face. And then layer 3 is even coarser, but information is aggregated right now, and supposedly only the most important information for prediction. I think this task was predicting gender of celebrity. So now it's all grouped together. Well, but there is also a layer, as we spoke about before, which is called pooling layer. So we generated our channels, but we know that our stride was 1, and we were moving just like that, and whatever we summed up in the first square and whatever we summed up in the second square only since the weights are the same, only differs by that shift. Oh, actually, this additional pixels that the first so these pixels that this first filter didn't see. So very small difference actually. In the output, lots of nearby pixels are correlated in the output channel right here. So imagine this is the output channel feature map or activation map, and what max pooling does is clearly animated here, without stride, without overlap, or actually full stride, without overlap, tiling the full feature map, the full activation map in the square or filter size, which is set by hyperparameter. Just selects the maximum element and pulls it to the following. Okay, pulls it to the following stage. to the following layer channel. This is the same max pooling, only opened up. So the interesting part, we select a max number, but just a maximum number in this area. This particular max pooling picture actually done with a stride, but you can decide for yourself how to do it. It's a hyperparameter. So max among a three array, but then we need to take just a side note. Interesting, when we do backprop, we need to differentiate through max. What do we do then? Turns out we only care about that maximal element that actually took part in everything upstream from this part now on. So when we are differentiating backwards, we only are computing derivatives and adjusting values that correspond to that maximal element. We do not pass the gradients through or compute the gradients through other elements, because anything smaller than the max, their tiny infinitesimal changes will not affect the max choice. It'll still be the same. So just on a side. Another type of pooling is average pooling, when that is clearly differentiable with normalized sum, or sum with a factor. So easy to differentiate, linear function. So what we have here is average pooling, average pooling. Every element is added together, 3 plus 3 plus 2 plus 1 plus 3 plus 1 plus 2, 9, 10, 15, right? Yes, we get 15, and then we divide 15 by 9, and that's when we got 1.7. So let's move on. We know what the pooling operations are and how they work. Now let's look at another thing. How do we produce a class prediction? If our output layer, so imagine we started here with some interesting image of a smiley face, and we went through the first convolutional layer right here, produced 2D channels, a lot of them, then went on, produced more and more, and so now we are here somewhere after many max pooling and other types of operations, and we have a lot of channels or feature maps that are activated. They carry some information about the input. So what do we do here? So one way to do it is to just take this all and vectorize it into a vector. Just say take this, that, this, like take all of those elements one by one and put them here. Take another channel, put it here, and then once you have it, you can put a feed-forward network, another feed-forward network. So basically this operation is flattening, right? Flatten and put into it feed-forward network and predict either phase or emotion, neutral. neutral, sad, and angry. But these channels, so all of the operations from the input up to here, the layer, the last convolutional layer, are convolutional, or all of them are convolutions. But then we flatten them and produce sort of slap feed-forward network and produce a classifier from the convolutional neural network. Okay, now we're ready to move to the next part. Well, not part, a building block. One convolution. What is that? It's just a single weight. Like right here, you take this value, you multiply it by some weight, say 0.3, and then you produce an output. That's kind of dumb, right? Well, maybe, but notice this is learnable. This is a learnable parameter. So what we can do when we are at this last layer, last convolutional layer that we just covered, what we could do, instead of flattening it, we could put one convolution. Don't confuse this with one-dimensional convolution. One convolution is not 1D convolution. So if we put one convolution here with only one neuron, we will stitch or produce a weighted sum, learnable, so then optimal, and just produce one layer that contains information, or one channel that contains information about all of these channels together, and then this could be flattened. So then we could, in such a way, we could reduce dimensionality in a much smarter way than simply flattening this whole thing and learning with a feed-forward neural network. The next building block is up convolution. Up convolution solves the following task, and you can see the animation here in this corner, while the same animation is kind of laid out in the center of the screen. Imagine you have an image and you want to upsample it. So instead of 2 by 2, you want to create 4 by 4. How do we do it in a learnable way? So our filters are trained on the images that we have, and they produce a larger resolution images from the lower resolution images. This picture diagram illustrates it. So we'll take a large filter and we convolve it in the following way, but we convolve it backwards. You take one input, multiply it with all values of the filter, and open up into a larger patch. And with overlap of this larger patch, you create an image of desired size when the filters overlap. And well, here you can produce a crop. You can crop the result if you need. But the important part is that you can upsample your image, and you can train the filters to be able to upsample your image. That's up convolution. We'll come back to it. Another building block, another element is dilated convolution. Dilated convolution is very important, actually, an interesting idea for the following reason. Imagine, let's just consider one-dimensional convolution. So we have three elements in our kernel, and we produce our first channel. Then again 3 elements in the kernel, and we produce another channel. Then again 3 elements. So look at this point, this neuron, this activation, or this whole neuron when it scans through. If we compute or draw, how I'm doing right now, this neuron right here sees those 3 values underneath on the underlying feature map. But if we continue, those 3 values were computed from this 1, 2, 3, 4, 5, and they're correspondingly were computing from the 7 pixels, input pixels underneath. Notice the following, that the first one sees 3, the second layer sees 5, the third one sees 7, and how far in depth you need to go in order to see, most of the image or the whole image. 100. This is traditional convolutional neural network. The receptive field grows very slowly as a function of depth of the network. So you need to go deeper and deeper in order for your output neuron to be able to see larger field of view. Dilated convolution, and those are all parameters. So you have more and more parameters with each step, because it's linear. Since you have lots of layers, it's 3 times each layer. Well, it's also times number of channels. What dilated convolution does, it says, okay, let's start maybe with a 3 by 3 convolution, just like that. But then, instead of going with larger convolution at next layer, we still use a 3 by 3 convolution, but we will only leave, we'll leave holes, skip or open up our parameters. So now our network sees 5 by 5 receptive field. Field of view of this neuron is 5 by 5, but it still uses the same 9 parameters as before. If we dilate a little more, leaving the gap of 2, then we see 7 by 7, and yet still using just 9 parameters. So this dilation with depth, by doing that dilation with depth, we can greatly expand the field of view of neurons at a deeper layer much faster than a regular convolution would do that. And because of that, we won't need as many layers and as many parameters in order to learn. But another one interesting thing is that think about that signal in 1D. If we are convolving that signal with this function that has gaps, then this function will only be able to see, just by Nyquist sampling theorem, right? It will not be able to see it's like a sample downsampling the signal. It's not sampling the signal at the rate that would detect slower frequencies. So the larger the gap, the lower the frequencies, or the coarser, smoother is whatever the neural network sees. But if you imagine that the first layer does not have a gap, the second layer has a gap or dilation in the receptive field, and another one has a gap as well, we will have a phenomenon when a neuron up top sees something underneath in laser focus, but then sees smoother the parts adjacent to it, and then even smoother and smoother until they just run out, run off away from the receptive field or field of view of this neuron. But that's how we see, right? We have a focus where everything is sharp, and then we have blurred but informative details at the edges. So what dilated convolution does, it allows the network to achieve that property that the neurons up in the deeper layers laser focus see only locally, but they have also global information available. And for most or a lot of applications, that's enough. We don't need to see everything in focus and simultaneously. It's enough to be focused on one local part. And by the way, this is not attention. We'll get to attention. This is dilated convolution and simple principles of signal sampling and Fourier transform, basically. It's related to it. So, take home. You need to know and be comfortable with the following concepts. What is a convolution with a kernel or a filter? How it works, how it produces a channel, how it produces an output, how it scans through the input. You need to understand why padding is used in convolutional neural networks. What is same padding, what is full, and why either of them would be used or why none. What's the difference between those? Then how kernels produce channels is important. How many kernels is each kernel is corresponding channel, and how a kernel takes multiple channels as an input. Please be comfortable with that. That's very useful, and that will give you an insight and intuition why CNN doesn't work on any of the applications. So pooling, also important. That's a way to throw away unnecessary information. There are others, but that's a very powerful one. And then how to go from convolutional layers to predictions. Let's correct that. What is one convolution? Also a useful tool. And what is dilated convolution? And then what I'm missing here, also up convolution is important. That's it for the building blocks.